possibly. Could be. Possibly. What does YouTube say about it? I am not seeing it. Ah, yes. Here we are. Nope, that's not what I want. Here we go. All right. Sorry about that. YouTube is more confusing than it should be. All right, so today I want to talk about some fundamental things. I know finals are coming around for a lot of people, and semester tests and all of that. So I want to talk about the formal definition of a derivative. Formal definition of derivatives. Conceptually, if we have a function and we want to know what the slope of the tangent line is at a given point, then we take the derivative to get the slope. Now, since we understand how to find slope of a line, we can do that with the derivative, or we can do that with a curve and approximate it iteratively. So if we say I have some function of x, switch back to the correct color and size, f of x equals something, then the derivative of that function is equal to, well, let's go back to our slope. M equals y2 minus y1 over x2 minus x1. So we need the value at x2 minus the value at x1 divided by x2 minus x1. Okay, so what is x2 and x1? We care about 1 point, not 2. So what we're going to do is we're going to say the point of interest plus some h and x plus h minus x. Well, now we can simplify a little bit. Can't do anything with the top. But on the bottom, we have x plus h minus h. And since this is all addition, there's no multiplication on that bottom side, we can get rid of these parentheses. And now if you have an x minus an x, well, that's 0, so you're left with h. But this isn't actually f of x. This is an approximation of the derivative. What we actually care about is the limit as h goes to 0 of f of x plus h minus f of x over h. Now, if we have a function, say f of x equals 3x squared minus 2, well, you know what? I'm lousy at polynomials, so I'm going to pick one that's a little easier. Yes, we'll go with that. Then when we go to do this formal definition, we'll say f prime of x is equal to the limit as h goes to 0 of f of x plus h, which is just x plus h squared minus 4, example. And that's this bit minus x squared minus 4 divided by h. Now we're still taking the limit as h goes to 0. So we'll expand this out. So x plus h squared is x squared plus 2hx plus h squared minus 4 minus, and we'll distribute the negative in, so negative x squared plus 4, all divided by h. I'm writing crooked. Rotate the drawing pad. Now, we still got the limit as h goes to 0. And we have x squared plus 2hx plus h squared minus 4 minus x squared plus 4, all divided by h. Now, x squared and negative x squared go away. Negative 4 and positive 4 go away. So then we have still the limit as h goes to 0 of 2hx plus h squared over h. And we can actually factor the h, so we end up with h times 2x plus h over h. Well, now we can cancel those h's. And this is valid because we're doing a limit. If this was regular algebra stuff and we weren't taking a limit, then we would have to say this is true except for when h is 0. But because we're never actually getting to 0, only as h approaches 0, we can do that. So now we still have our limit. Let's write neatly. H goes to 0 of 2x plus h. Now we can evaluate our limit and do 2x plus 0 equals 2x. And that is our final answer. Now, if you know the rules from later in calculus, you'll know that we have an easier way to take this limit, or take this derivative, which we can use to check ourselves. And so that's going to be f prime of x equals, and we'll use the exponent rule, so we bring the exponent down and subtract 1. So we'll put a 2 there and subtract 1, which gives us 2x. And then the minus 4 is a constant, so that's a 0, and we're left with 2x, which is exactly what we got. So we did it correctly. that's really all there is to it on the formal definition of the derivatives. I had somebody request that we do some machine learning stuff. And while I'm not ready to do that, as that's a little bit entailed, it's a lot entailed, I will start working towards what we need to know to do that. So let's do something called the chain rule, which again is a calculus thing, and you probably are familiar with it if you've had calculus, even if you're just in Cal 1. So the chain rule says that the derivative no, that's not how I want to write it. If you have a function f of x equals something and g of x equals something that are both differentiable and continuous, then the derivative of f of x times g of x, that's the product rule. That's not what I want. F of g of x equals the derivative of the outer part evaluated at the inner part times the derivative of the inner part. Well, that's confusing, I hear you saying already. Yes. Yes, it is if you're just looking at it that way. But we can look at it a little bit easier. So if I have a function, let's suppose f of x equals 2x and g of x equals x squared. Now you're telling me that's not hard. If I do 2 times x squared, well, the derivative of that is just 4x, because you use your exponent rule, you bring the 2 down, you multiply the 2's together, and you got 4x. You would be correct. However, we can do this with the chain rule, because that's actually what you're doing here. It's just not obvious. So let's do it with the chain rule. We'll label this as intuition. We'll do it over here with the chain rule. So f of x equals 2x, g of x equals x squared. We want to find the derivative of f of g of x, which is 2 times x squared. So we'll take the derivative of the outer part, which is 2, because f prime of x equals 2. The derivative of the inner part is 2x. I'm going to color code things because I can. So the derivative of the outer part is going to be 2 times derivative of the inner part equals 4x, which is what we expected. Now let's do a little bit more complicated one. So if we have f of x equals sine x, g of x equals e to the x, f prime of x equals derivative of sine is cosine, derivative of e to the x is e to the x. So if we want the derivative of the composite function, which you may actually also see written that way. That's the same thing. It's just written a little different. So that's going to be sine of e to the x, which is actually a fun graph if you get to look at it. I think I can plot that for you here in a little bit. Derivative of that is derivative of the outside, so cosine, derivative of the inside, no, times the inside, let me say that again. The derivative of the outside composed with the inside, so e to the x stays there, times the derivative of the inside, which is e to the x. So our final answer is e to the x, cosine e to the x. And if we bring up our graphing calculator, graph me. Leave. We can enter it here. So this will be e to the x times cosine e to the x. Display. X-axis is fine. Y-axis, we're going to go negative 100 to 100. Negative 10 to 10. Why are you doing that? Negative 10 to 10. There we go. And so e to the x gets bigger and bigger and bigger as x gets bigger. So this coefficient out front controls how big the amplitude of the wave is. So it gets bigger and bigger and bigger. And this thing inside controls the frequency. And as you have a higher number, as you have a bigger number, the wave gets squished more and more and more and more, so it gets higher and higher frequency, which is what we see. If we were to change the function to be decreasing, so if we changed it from nope, no, that one, and that one, and that one. Yeah. Well, actually, no, let's do another example, because we can. And I've come up with one that will look cool, I think. Let's do another example. So let's do f of x equals 1 over x. G of x equals cosine x. I'm being all fancy on you. And then we'll do another one, h of x equals e to the x. Right? So then we will do our chain rule. I'll write it again so that we can see it. The derivative of f composed with g composed with h of x equals that. That's what we're trying to find. Hang on. I'm getting ahead of myself. I'm about to sneeze. Kind of sneeze. Alright, so this is what we're trying to find, and this is the rule we have. So what we're going to do is break it into stuff we know. So what this combined function is will be not the function I meant for it to be. I will erase this and make it into the one that I want it to be. F composed with H. Okay, that's what I want it to be. So G of F of H of X. Now, let's go ahead, find our derivative pieces, because that's easy enough. So f prime of x equals the natural log of x. G prime of x, if the derivative of sine is cosine, and then the derivative of cosine is negative sine x, and then h prime of x equals e to the x. I want that to be a negative, and that's negative e to the negative x. And I'm changing the problem on the fly because I'm trying to make it look like something in particular. The process I'm showing you is good for no matter what problem you're doing. And I'm going to recommend not changing the problem on the test. Okay. So if this is what we're trying to find, then first we should probably find the function. G composed with f composed with h of x equals cosine of, you know what, I'm going to back up and color code because it's going to make it easier to follow. G composed with f composed with h of x equals cosine of 1 divided by e to the negative x for clarity. I'm putting that there. Which is equal to the cosine of e to the x. Yes. This is not what I wanted. Because that's exactly the same as the one up here. Only it's a cosine instead of a sine. Let's change this again. Let's see. What will make this do what I want it to do? I think I can keep that all the same, but I'm going to change it to G of H, F, which is what I had in the first place. Okay. F composed with G composed with H of X that needs to be yellow. Is equal to 1 divided by cosine of e to the negative x. So that's our function that we want to find the derivative of. Now we can rewrite this a little bit and do cosine e to the negative x. Negative 1, not to be confused with the inverse function. That does get confusing. It's an unfortunate notation, but it's one we kind of got to deal with. Now, if we want to find the derivative of this function, we'll call this gamma of x. That way you can say you use Greek letters in your problem. And the first thing we're going to do is we'll take the derivative of the outside So that's going to be -1 times, no it's not, it's going to be the natural log of whatever's in the middle. So cosine e to the negative x. Absolute value? Yeah, it is. Times, I should do this in red. Nope. Natural log, the absolute value of cosine e to the negative x times, then in yellow, the derivative of this inside piece. So the derivative of cosine is negative sine of e to the negative x times the derivative of the inside on the last leg. Derivative of e to the negative x is negative e to the negative x. Now, we can start combining things a little. So we'll have natural log of the cosine of e to the negative x times negatives and the negative cancel out. You're left with e to the negative x times the sine of e to the negative x. All right, and so now we can actually ask ourselves an interesting question, which would be, what is the value of that function at infinity? So let's figure it out. And I want to do this before we go and plot it. So let's take the limit as x goes to infinity the natural log or the absolute value of the cosine of e to the negative x times e to the negative x times sine of e to the negative x. Now, we actually can't, I don't want to say we can't do this analytically using math notation, writing it all out, but it's going to be way easier if we just look at this and go, okay, we're going to have this and this inner pieces. Different color. This. Those pieces are going to bounce back and forth. That's the nature of the trigonometric functions, is they go back and forth. And these particular ones go between -1 and 1. No matter what x is, the value of sine of e to the negative x will be somewhere between -1 and 1. The value of cosine of e to the negative x will always be somewhere between -1 and 1. E to the negative x, however, will shrink. And so if you're multiplying all of these numbers together, let's deal with this part first. This part first. Sine x, and I'm actually going to say sine a, for all values of, is what the upside down a means, a in R. Right? So e to the negative x e to the negative x times sine of a of x is going to be less than or equal to e to the negative x. Is that correct? Yes. Yes, it is. Because we're never going to make, because sine, the magnitude of this sine e to the negative x is going to sit between -1 and 1. It will only ever make a number smaller in magnitude. May change the sign. Yeah, may change the sign, but it will never make it have a larger magnitude. E to the negative x is always positive, so we can say this is true. Yeah. Now we can do a similar thing with this natural log portion. Natural log of the absolute value, because -1 is irrelevant here. That's interesting. This function is going to be undefined for any places where cosine is negative. Interesting. Oh, this is going to be weird. Okay, natural log of this number, and we're going to deal with the positive portion. So absolute value of cosine of e to the negative x is greater than 0 and less than or equal to 1 for all here as well for all a in the real numbers. Okay, now this is odd because here we're going to have the natural log of this bouncing value. So natural log of that, right? Now, natural log is not defined at these points. So we're technically breaking some rules here by trying to take the limit as it goes to infinity of a discontinuous function. Which is not allowed, technically speaking. But we're going to do it anyway, because we kind of can. So what we're able to do with this limit is take a shortcut and say it's the same as finding the limit as x goes to infinity of, and I'm going to simplify this one piece at a time, of that. Now we want to take the limit of this part, but the natural log of this bouncing value is going to have an upper and lower bound. Now the problem here is the upper bound, lower bound. The lower bound is when cosine of e to the negative x is 0. Problem, the natural log of 0 is negative infinity. So it has no lower bound, but it does have an upper bound, and so we're going to deal with the upper bound. Yeah, we'll have to put a caveat on this later. But the upper bound is the natural log of 1, which is 0. This is going to be funky looking. Of 0 times e to the negative x equals 0. So this is actually the limit of the upper bound. The limit of the lower bound does not exist because, like we discussed, the natural log of 0 is negative infinity. So this is abusing notation horribly, but I'm just putting it this way so that we remember all the stuff. Lower bound. So this function, the derivative of our original function, is going to be looking something like this. Down at the bottom, way out here at infinity. So I'm going to put a... Nope. It's going to look like... I'm struggling to think here. I think it's going to be a discontinuity. And it's going to be gradually shrinking towards 0. And back up here in the middle, I have no idea. So let's see if we can make this work. I have my doubts. But we will give it a go. So we will have the natural log of the absolute value of cosine of e to the x times e to the x times sine e to the negative x. And this actually needs to be a negative as well. And if I say display, they're going to freak out. Can I say log? No, it doesn't want to. All right. Wolfram. Wait. Yes. Wolfram Alpha. This is, oh dear. Back. Nope. Please stop. Oh dear. Did I crash it? I might have crashed it. I believe I've crashed it. Hang on. Got it. Okay, let me try something else. Alpha. Computational intelligence. Graph of absolute value of cosine e to the negative x times e to the negative x times sine e to the negative x. Yeah. So all of these graphers online, almost, or a bunch of them anyway, don't like it, this function. Does the Google one work? Yeah, I know. Yep. Yes, it does. You can kind of see it here. Can I... Nope. Well, this is the graph. Just trying to figure out how I can make it bigger, but it doesn't want to. Oh. Okay, so let's go back to the board for a second. I messed this up right here. This is not correct. All the math was correct. That's not correct. The reason being, this e to the negative x inside this scalar is stretching time out so that it takes far longer for it to reach 0. But eventually it will, and then it will go down like that, and come back up. Way out there, and that will happen periodically. I was gonna put the graph in here, but that's not gonna work. We can do the graph of the original function though, which is the one that I spent that time trying to make it work the way I wanted it to. This one. Here we go. And so this one is going to be 1 divided by the cosine of e to the negative x. There it is. Display. So it's crazy out here where it's super high frequency, but because that descending term is over there, that one behaves. But it looks like we have a limit here that's non-zero. So let's see if we can find the limit of that function. Because now I'm curious. So what is the limit as x goes to infinity of 1 divided by cosine of e to the negative x? Well, e to the negative x approaches 0. So that would be 1 divided by the cosine of e to the negative infinity is 1 divided by cosine of 1 over e to the infinity cosine of 0. Cosine of 0, of course, is 1, so that's 1. So if we hover over it, does it say that the value is 1 or approaching 1? Yep. Cool. If we change this to be no, that just gets more and more crazy. Cool. And so I can imagine that since I put this in the context of machine learning, that you're wondering why on earth is this chain rule relevant? And the chain rule is relevant because when you create a neural network, you have one layer feeding into another layer, feeding into another layer, and sometimes you've got splits and weird stuff going on in there. But essentially all it ends up doing is creating one big function, that's made up of a function of a function of a function of a function, all the way down the list. And when you calculate forward, you just multiply everything together. Multiply everything together. Your functions are composed primarily of multiplication and addition, so that you don't have weird stuff in the middle. You do have activation functions, and those can sometimes cause weirdness, but it's largely just multiplication and addition, and you're just composing those functions together. That's fine for feed forward, but in the back propagation step where you go, okay, this is what my input is, this is what the output should be, this is while you're training. Output or input up here, output comes out down here, and you have a label. And so then you compare the output of the network with the training label, and you take that and you take those two things and you create a different, or you create a an error or a cost, and you say, okay, I have to correct it by this much, and you take that error number and you back propagate it up the network. And when you do that, you change all of the weights a little bit at a time, and you figure out how much to change those weights by using the derivative. So it's important to know A, derivatives, but more importantly, B, how the chain rule affects your formulas. So that you can make sure all of the weights change appropriately. There's more to it because you end up using matrices and vector math to get all that to work out nicely and quickly on a computer. I am not yet comfortable with how that math works for multi-layer networks, and I want to be able to show you both a specific single layer case and a general case. So I will work that out at some point, and I will probably put that into a video, not a live stream. That way I can make sure I get everything right the first try. I think that's going to do it for today. If this video was helpful at all, if you learned something, be sure to hit the like button, hit subscribe. I try and stream just about every week. Probably going to take a break over the holiday so that I can hang out with family, but also because most of you aren't going to be in school, and if you're not in school, you're probably not spending time learning this stuff, which is fine. So I want to let you have time to hang out with your families and everything too. So yeah, be sure to hit the like button. If you have problem requests or things that you want me to work on stream or in a video, or if you just need help, I can try and help you in the Discord chat. Join the Discord, put your problems there, and I'll pull from that. Instead of making stuff up as we were going, I'll pull your homework problems and work them in the stream. Other than that, I think we're good. So